The purpose of this screencast is to discuss the concept of dislocation and plastic deformation. So let's say that you have a bowl of cold ice cream and a spoon. So if you go ahead and take a bite out of the ice cream and you put your spoon in the ice cream and it bends, but it does not go back to its original shape, what you have just experienced or what you have just observed at the macroscopic level is a large number of dislocations moving. Another way that we end up describing this is plastic deformation. So let's go ahead and take a look at what a dislocation is. So if we have a metal that is solidifying, we're going to expect that during solidification, it will actually end up forming for us a lattice. So sometimes the lattice that ends up forming has a defect in it. And these defects are what we call dislocations. So if our defect is a situation where we end up having part of the plane not forming, we end up calling this an edge dislocation. And you can see how our lattice has a missing atom. So in yellow is where our missing atom is. This becomes a problem if we end up having a situation like our spoon with our ice cream. So if we go ahead and we place a force on the side, and this would be similar to if we went ahead and dug that spoon deep into that ice cream, what we'll end up finding is that our bonds along plane 2, so right along this plane, they start to stretch on us, and then they'll eventually break. And once they end up breaking, we end up having a situation where right at this point, you will find that these bonds are going to actually end up breaking and reforming and allowing us then to have plane number 1 will end up having a full plane. The result is that your defect in your material in your lattice is now moved. It's no longer along plane 1, but instead it's along plane 2. If we keep applying our shear force, what's going to end up happening is our dislocation is going to keep moving. So our defect will keep moving all the way to the end. So then we're going to have a situation where our final lattice will end up looking like this. In this case, our edge dislocation has moved all the way to the end, so now it's in plane 4. One of the things that's really good to remember, though, is that what you're seeing here is a single dislocation moving. This was all we had in this example. However, anytime we see plastic deformation of a metal, we are seeing several dislocations, large numbers moving all at once. So a little bit different than the example that we have here. So the definition of slip is plastic deformation through, or produced rather, by dislocation motion. Another concept that's associated with dislocations is this idea of dislocation density. So as our materials end up solidifying, we end up having different types of dislocation densities associated with that metal. So dislocation density is defined as total dislocation length per unit volume. What you'll end up finding is different type of processing that we do actually will increase our dislocation density. For instance, processes that can increase your dislocation density would include cold rolling. Another process that may end up increasing your dislocation density would be cold forging. In these cases, we're assuming that our material is above its recrystallization temperature. We're assuming that our material is below its recrystallization temperature. So for cold rolling and for cold forging, these are examples of processes below recrystallization. So just remember, the next time you end up permanently deforming a metal, what you have actually done is a large amount of dislocation motion.